and welcome. Welcome to ASMR Chemistry. I'm Professor Karen Ullman, here to teach you a little bit of chemistry or help you go to sleep. And I wanted to, today in this video, go slightly more advanced, but it's a topic that comes into many chemistry classes. And I got a request for it, so I want to honor all requests that I get, even if it takes a while. So we're going to get to play with this molecule set and build the molecules first. Then I want to talk a little bit about the electrons in these types of molecules and why they're so special. So what we will be talking about is coordination chemistry, which is where you have a metal center. And when you have metals in compounds, it makes things a lot more interesting with the bonding. So I'm going to move my paper out of the way for a minute. So that we can focus on the molecules that we're building. So we are going to be looking at when a metal is bonded to 6 things, usually nonmetals. It is possible to have bonds between metals, but we're going to look at when there is a metal center and it is bonded to 6 nonmetals. In this particular compound I'm going to make, we'll have 6 chloride ions bonded to it. Now, you might ask, what's the metal in the middle? Well, this type of bonding can happen with many different types, many different identities of the metals. Let's just remind ourselves of the periodic table. And we're really focusing on this central area here. These are called the transition metals. And this is where the d orbitals are getting filled. If you have not learned about d orbitals yet, that's okay. It's a place where the electrons go. So you can think of orbitals as electron clouds, where there's a probability of finding an electron. Okay, so we are focusing on some of these elements. You'll recognize the names, such as chromium or cobalt, nickel, iron. Many of those are common, as well as these larger ones down here: platinum, gold, mercury. All right. So it's very common for these metals to be able to bond to nonmetals. I'm going to choose green to represent chloride. 6 of them around. So I wanted to mention the d orbitals because these are places where electrons can be found. And it's actually quite important to know a little bit about these orbitals in order to understand interesting properties about metals and these metal complexes when the metals are bonded in ways such as what I'm showing here. Because you get very interesting colors of these compounds, and you get interesting magnetic properties, things like that. Okay, so let's close up the model kit for now and set it aside. Okay. So if we were able to zoom in and see what a metal complex might look like, we could see that if we have this type of shape, this is called octahedral. It's a very common shape that you get for metals that bond to nonmetals in this way. There's also tetrahedral. There's also square planar. But octahedral is very common, so we're going to talk about that one. So I'd like to focus on, let's just say, there is a chromium metal ion is the central atom. And I'm going to bring my pens over. And let's draw the energies of the d orbitals. That would exist for this chromium metal in the center. Okay. So let's imagine we've got our chromium metal, and we are going to, I feel like it needs to be darker, maybe thicker. I'm going to use a different pen. I think this one will be better. Okay. Yes, okay. All right. So here's our chromium. And we are going to assume that this is a chromium ion that is positively charged +3. Okay. So when a chromium ion is +3, that means it has an electron configuration that is argon, and there are 3 electrons remaining in the 3d orbital. So these are the valence electrons. Okay. So all those electrons, there's 18 of them. Those are the core electrons that have the same electron configuration as argon. So these three, this is where the interesting stuff happens, okay? So if we just had a chromium ion floating around in space, and we were interested in the valence electrons, the 3D orbital, there would be 5 of them, okay? There are always 5D orbitals. And again, if you haven't learned about orbitals yet, you will. You'll learn this. Okay. There are 5, always for D. All right. And there are 3 electrons that are in those D orbitals. So these little arrows here represent what we call spin-up electrons. Okay. Their spin quantum number is a +1/2. Spin up, spin up, spin up. And when we separate them into the orbitals, this is following what we call Hund's rule. Hund's rule, where the electrons are more stable if they separate out into different orbitals first before they pair up. Okay, so this is what we would observe if it was what we call a free ion. Okay, that would be the metal in the center not bonded to these nonmetals. Okay, so meaning it's free, it's by itself. Okay, but now if we were to have this chromium, it's still +3, and it still has 3 electrons. But now it is bonded to 6 chloride ions. So now, overall, this whole complex is -3. Okay, do you know why that is? Why would this whole thing be -3? Well, if the chromium is +3, and each of these chlorides is -1, and there's 6 of them, that means overall, this charge would be -3 for this complex. And what happens is this actually splits in energy. Now, in another video, I am going to go into greater detail on this splitting. And I want to do that where I can draw out these d orbitals and what they look like for you, so you can get a better idea why they split in this way. Okay. But these two, if you're curious, specifically, these are the dz squared and dx squared minus y squared d orbitals. And these 3 are the dxy, dyc, dxc. Okay. These 3 electrons will follow the Aufbau principle, where they will fill the lower energy orbitals first before filling the upper ones. Again, I will, in a future video, give some more examples of how this plays out. Because what if we had 5 electrons? Where would those go? Would they be all down together and pairing up? Would they spread themselves out? We can answer those kinds of questions. Okay. But in this case, we've just got these 3 electrons, and they will go down here. Okay. So these electrons can absorb light and get excited up into these higher energy levels. And it just so happens for many of these metal complexes that they are brightly colored. They're a whole range of colors within the visible range. As we see red complexes, yellow, blue, green, orange, violet, every single possible color. Because it just so happens that the difference in this energy level here and this energy level here, so this difference here, I'm just talking about difference in energy, not an arrow to represent an electron, but just a difference in energy. Change in energy. This is referred to very specifically as delta naught. Actually, I'm sorry. I corrected myself. That is not a naught. Naught means 0, right? This is O. O for octahedral. Okay. So if this were tetrahedral, that would be a T there. Okay. But notice that this could also be equal to the energy of a photon, which is equal to Planck's constant times the speed of light divided by the wavelength of the light. And the wavelength is often in the visible range. Which is the reason that so many of these transition metal complexes give us beautiful, vibrant colors. For example, cobalt blue. These cobalt blue complexes are quite lovely. And copper, we get some bluish colors, some green colors. Iron, we get orange, right? With iron oxide, which is rust. And there are many other colors that are possible. So as a reminder, I'm not talking about what the metal looks like by itself. So where platinum is a silvery color and gold is more of a yellowish gold color, right? Those are just the metals alone. Okay, they're just bonded to other gold atoms or other platinum atoms. All right. So those properties you have for pure metals, they're different than what you get when you have a metal that's bonded to these non-metals. So this is a whole special subcategory of chemistry called coordination. Coordination chemistry. This is where metals bonded to nonmetals in lots and lots of very interesting ways. It's quite marvelous. This is just one example of so many, uncountable. Because just imagine you could have, here we have 6, all the same, all these chlorides. But we could also have 4 chlorides and 2 ammonia molecules bonded here and here. Or here and here. Or any number of so many different nonmetals, either nonmetal ions or even molecules. So this field is enormous, and it is so important for our world and for biochemistry. The iron in our blood, hemoglobin, it's all based on coordination chemistry. In hemoglobin, we have iron in the center, and then these nonmetals around here are part of the protein, the hemoglobin protein. And then we have our oxygen, O2 molecule bonds here. Okay, many examples. So I just wanted to give you this as a kind of an introduction, maybe pique your interest a little bit in coordination chemistry. So thank you, as always, for joining me, for liking the video, for subscribing, for all of your support, all of your kind words. I love making these videos for you, and I will continue to do so. And also feel free to share these videos with anyone you think who would enjoy learning a little bit about chemistry, or if they enjoy ASMR. And maybe this is so incredibly boring it will help them fall asleep, which is also very important for us humans, isn't it? So, thank you, as always, and I will see you in the next video.